So in this last section for today, we have another very exciting lecture by our lecturer, İnanç Adagideli from Sabancı University. So Professor İnanç Adagideli is also part of TÜBİTAK Research Institute for Fundamental Sciences as a senior researcher. He is going to give a lecture entitled Topological Matter for Topological Quantum Computing. İnanç Adagideli received his MS in Physics and BS in Physics and Mathematics from Middle East Technical University and his PhD in Physics from the University of Illinois at Urbana-Champaign. His research interests include theoretical condensed matter physics, topological quantum computation, spintronics and spin-Hall effects, as well as topological insulator and superconductors, mesoscale and nanoscale physics, quantum transport theory and quantum electrodynamics. Professor İnanç Adagideli is the recipient of TÜBİTAK Science Incentive Award. With this, I want to invite to the stage my remarkable colleague and friend to begin his lecture. İnanç Hocam, please come and begin.
Thank you very much for the kind introduction. So it's a pleasure to be here to given this option to give a talk, give a lecture. I would like to share I would be sharing from two places. I hope I can do it. Let me just try this. Let me try to share my screen. See if that works. I think, yes, that works indeed. So, so today I would be talking about, let me just get rid of this. So today I will be talking about topological matter, and tomorrow, basically, I will be talking about how you can use kind of some of the ideas that I, talk about today and use them to do some protected computation. So, and by the way, I would like, if you have any questions, please don't wait, just type it right away, and I would rather that I answer it right away. And actually, I will actually even have questions for you. So we'll see how this develops. So the idea is, what I would like to do is the following. So I would like to start with, the usual, well, the free particle, right? So this is basically on topological matter. Unfortunately, I realize it's a very ambiguous undertaking for 2 lectures, so we'll have to see how do we do. So I would like to start with a free non-relativistic particle of mass m, right? So we know the Hamiltonian is p squared over 2m, right? So I hope I'm not losing half of you. So those of you who got quantum mechanics or classical mechanics, Hamiltonian is the total energy. I have no potential, so I have a non-relativistic particle. So hence the energy looks like this. Right, so this is the energy as a function of momentum, and I have something like this. Right, so this is basically a p squared over 2m. Now this is for a real free particle, but if I actually look for a lot of the semiconductors or a lot of the metals, when you actually have crystalline, basically have this crystalline structures, you have this repeated space filling potentials. So now you actually see that your band structure doesn't have to be this simple, but they will always have these points where actually everything looks like this p squared over 2m, certain points in your momentum space. But the only difference would be that you would have a m star. So now always there's something that, like you probably heard this, also this episode of Big Bang Theory, where, and if you didn't, you probably heard it when there was all this ruckus was happening with graphene. So we were talking about a particle which had no mass. So now that's a very hard thing to answer when you're looking at your classical, or at least non-relativistic Hamiltonian, because you see that you look at this and then you think, hey, how can I actually make the mass zero? Right? The funny thing is that you can actually make the mass negative, right? It's an easy thing to do, and we actually see it also in our metals and semiconductors. You actually can have a situation where you can actually have, this is the top of the conduction band and some sort of, and then you have here's the top of the valence band, the bottom of the conduction band. And then you basically have another one here, and you have here minus, your energy is minus p squared over times sum 2m star, let's say whole. Okay. Now it's very easy at this point, but you can imagine a negative mass, but you cannot really imagine zero mass. That's not a fun situation. So actually the problem comes in because if I actually sit here, right, at a certain momentum value, and then start increasing the mass, right? If I start increasing the mass, I would find out that my velocity, right, at a certain momentum p would go like p over, well, m, so we all know this. And then if that m star goes to zero, your velocity increases uncontrollably. Now we know that, of course, obviously, there's of course the limit, right? But there are also other energetic reasons where this is limited, right? So if you look, of course, obviously you cannot exceed the speed of light here, but even before that, typically, even if you're looking at the lower energy, some sort of excitation spectra inside of some metal or something like that, you also have reasons that you cannot actually increase your velocity too much, because that would be too, your band would be too sharp, you would be heating too much, generating too much big energies, and so on. So typically, if you actually ask yourself what would be the typical guess, right, we know that typically that our band gaps are of electron volts maybe, and then if you say that your h bar is somewhere like something like 6 times 10 to the 6 electron volt seconds, and your lattice size are, let's say, a few angstroms, you can actually come up with a ballpark number, something like 10 to the 6 meters per second for your velocity. It's much slower than the speed of light, but still considerably fast. But the point is, you cannot make your mass zero, because then as you get your mass zero, you will hit that limit. Right, so then actually you realize, well, that's actually a good idea, because if there's a limit, then all these guys would have to turn kind of flat as you go increase in momentum, right? Then you would actually have a situation where you would have an excitation spectral like this for zero mass, right? And then this would be for a particle of zero mass, and then as you get mass, then instead of having this little cross structure, you would have basically, generally a gap. So this actually, at this point, I would like to talk about a couple of things. So typically when we talk about mass, you might have noticed that people talk about slightly different things. So one thing is, of course, our good old relativistic mass, non-relativistic mass, right? What we always talk about. There is also this amount, what the condensed matter people, we would call that the gap, right? But sometimes this is equal to, of course, related to this famous mc squared, right? Sometimes called rest energy. So of course, even in the real electron would actually have a gap like that, even when it is free. And so that's why sometimes the gap is sometimes called the mass gap, and the value is sometimes people talk about gap when they talk about actually having some sort of a gap in your system. Okay. So now, the thing is that, of course, now I would like to talk about so then you would imagine that, can you ask yourself if you can, get a situation like this, like those two bands in somewhere in your momentum space actually touching at a certain point? And if they do, how would you describe that? Actually, describing is rather easy, because you see that from the quantum mechanical point of view, you basically have, let's say, you have basically at least minimum two quantum numbers, right? You have to talk about the upper band and the lower band, or whatever it is, right? So you would not have a single component wave function, because you have to be able to tell, after you told your that particle has momentum p, have to tell if you're in the upper band or the lower band. So that will mean that you would have to have some sort of internal degree of freedom, which looks like spin. And then you basically have, sorry, let me just come here. So you basically have here, with a massless situation, you would have a particle that goes to the right with this, speed that is limited, and we call that speed Fermi velocity, right? Something like Vf times P, right? And of course, you have to have two of these guys. So you would basically want to write it as that spin there. So I would like to use the Pauli sigma matrix. So I would like to call that VFP here, 0, 0 there, and then the one that goes exactly opposite minus VFP. Okay, so this is for the masses. Of course, then I would like to ask myself what gives you the mass, or if you want, in this case, the gap. Sometimes people call that gap the relativistic mass. So there's there's a lot of usage in this business that people keep, like it's actually all, I think, started from Schwinger's ex students, where they actually, Schwinger had a lot of PhD students, and some of them actually went back to condensed matter, doing a lot of like what they learned in high energy, trying to apply it to condensed matter, and then getting some of the stuff back out into the high energy area. And then during that time, there was a lot of, people talk about, then when they talk about mass, they did not talk about, you talk about mass gaps and things like that. Now the mass comes like this. And something that will mix those two bands together, right? So now, of course, you might say, why did I use so you realize that I've been using Pauli sigma matrices. You would realize I use sigma matrix X. There's actually a reason for that, and I'll come back to that later. So, but if you look at this Hamiltonian, this is a very nice Hamiltonian, right? So this is, if you want, sometimes called, so 1D, people call it Dirac Hamiltonian, right? It looks something like this: VF times P times sigma Z, plus you have a mass times sigma X. Right? If you look at the excitation spectra, it looks exactly like the previous picture. Now, the fun thing is that now you can talk about stuff like, what about the mass is negative, right? So if you talk about the gap, right? If you talk about the mass that we talk about non-relative thing, we only have an upper branch. We don't really have a second one. We don't have to worry about anything. So then mass being negative means that, you go to the other branch. Now here, mass being negative, you get the exact same spectra. Right? So you basically, if you do this calculation, you will see that the spectra is actually even, right? We actually know the energy, right? Energy squared is actually equal to Vf squared P squared plus M squared. Remember that M now has units of energy here, so that's why you don't have the usual Vf, whatever passes for C squared here. So now, so then you see that the energy excitation spectrum does not change. So what does change, right? So that's the key thing, and that's one of the overarching themes that I'm going to talk today. And one is that then you ask yourself, well, if I have that, let me just think about a case where actually I do make a quantum mechanical case. Let's just make that M as a function of X, right? This is a function X, and then let's say that it's coming from some constant here. Use a different color for that. Say orange, it comes up with that constant, and then it kind of changes sign along the way, and then it goes to another constant, which is, let's say, M naught, and this is minus M naught. So now we have actually two regions of space which has the exact opposite mass. So now, well, you can actually, so I would like to give you this homework, but I'm going to solve it right this moment to show you certain features of this. So the way that you do it actually is that, and I'm going to tell you what is the most important outcome of this. Remember, the mass gives you a gap, right? So you basically have an insulator. Now, and of course, the talk obviously is about insulators, but so then the important thing is that if you have a minus M, that also is an insulator. So then the whole point is that whenever you're attaching them together, if you get something interesting, and normally you don't, right? Insulators are boring stuff. A lot of things are insulated, right? All those dielectrics around you. You see a dielectric, piece of plastic looking thing. You throw it on another thing, nothing happens. But here, there's something really happens. And that happens is that turns out that you actually have a quantum state exactly at zero energy forming here, right? So we call it psi naught. So whenever you're looking at the spectra, right, for M naught, right, you have these band gap here, right? So you have this M naught and higher, you have states that are here, essentially minus M naught and below. And then exactly in the middle, you have this one very special zero mode. Right, this is basically a solution of the Hamiltonian, which has zero energy. So now you know typically if you say that if you have a reason to believe that your chemical potential is exactly at the middle, that zero mode would tell you that your ground state is degenerate. Right, so that's actually we're going to see that that's extremely useful if you want to do quantum computation. Now, how do I actually get this? And you know, is this like, you know, of course we know we're getting states at certain energies, and what is so special about zero energy? So now all in good time. So now the main thing is that actually, so the fact comes in from the following. So first of all, if I look at this Hamiltonian, right, this is the 1D Hamiltonian I have, and if I make this combination sigma y h sigma y, right, I would find out that this thing is equal to minus the Hamiltonian. Okay, so this is, you know, something that you could have come up with, but we will see that we are going to use that all the time. What this means is that suppose you have a solution of the H1D with some solution energy, with some energy epsilon, right? So there's a solution phi n with energy epsilon n times phi n. Now this tells you that if you look at this combination H1D acting on sigma y phi n, right? If you look at what this does, you actually can see that if you multiply it from this side as well, right? So you would find out that this is equal to, right, exactly minus H1D acting on phi n, right? And this is equal to basically minus epsilon n phi n. You multiply both sides with sigma y, then you get that H1D acting on sigma y phi n is equal to minus epsilon n times phi n. So it tells you that whenever you have a positive energy, you also have a negative energy. Okay. So this is a very strange thing, right? We don't usually know this from looking at your you know, Griffiths level quantum mechanics, because we have a definite choice of positive energies. Here we have positive and negative energies. We actually have a symmetry that actually combines them. So in semiconductors, you might have a symmetry like that, which could be approximate, but there are also other parts when in superconductors, this type of symmetries, not necessarily this one, but these type of symmetries, you would find out, we will see that they actually are sacrosanct, that you cannot actually break them. Right, so but when this happens, you see that zero is a very special point, right? So because zero, you actually can have of course, then the question is, suppose you have this zero mode and you have only one, right? I haven't yet shown you that if you have a zero mode or not, but suppose you have one, right? So now we have exactly one zero mode here, and there's only, let's say it is only one. Now the important thing is that suppose you do something to your system, but you know, so you change your M in various ways, but you still at all times, you obey this. As you obey that, you know that your spectra has to be symmetrical at all times, right? If you have a single zero mode, that cannot shift from any zero energy, because if it shifts up, you need a partner that negative energy. Right? So that is impossible because you have only one, right? Then you would have two states out of one state. So which means that the moment that you're stuck in one state, exactly at zero energy, that can never go anywhere. Okay, so whatever you do, that's kind of it's the notion, if you want, later on what people call the topological robustness, right? All the topological invariance. And the fact that you have a zero energy state is the topological, the number of such states would give you a topological invariance. Okay. So now, what I would like to do is that I would like to now show you explicitly as an example, right, how you can actually get this. Right, so it's very easy, but I may have to go a little bit quickly. So if you have any questions, please at this point type it. Now let's just look at this, my Hamiltonian. Right, this is my minus IVF del over del x times sigma z. Then I have plus some m of x times sigma x. So now what I can do is that I can make a global spin rotation, right? So I can actually use rotation where, you know, remember, there's nothing really special about sigma z, sigma x, and sigma y, right? I could have chosen, you know, so I can also look at it this way. So this is z, x, and y. If I make a spin rotation around x, right, to move by an amount pi over basically 2, right, 90 degrees. So you would get a sigma z, it will rotate to sigma y, okay? It's just nothing. Yes, as your Shojam question.
So this zero mode is robust. This is very nice, but it doesn't carry energy. So in photonics, we have just argued a few days ago that non-energy carrying excitation or things are not very easy to measure and not very helpful. But what's the situation for this?
Yeah, we will come back to that actually. So the important thing is that, remember, of course, there are actually two answers to that question. One is that, which I haven't shown yet, but remember, these are fermionic. I mean, the base here is fermionic. So what you do is that you measure charge. So whenever you make a measurement, and the charge measurements are extremely different from, let's say, measuring photons, right? When you make a photonic measurement, you absorb it, it's gone. When you make a charge measurement, the electron stays there, just passes through something. It's not like the energy is electrons absorbed somewhere and so on. So the measurement structure is extremely different. So there is, you know, that we have to put it aside. And the second thing is that if you want to measure this, indeed, you have to ultimately bring two zero modes together, and then you make an operation on their measurement operation on there. So ultimately, when they come together, they would actually hybridize. But the state of them would actually carry all the whatever individual, like this entanglement with the rest of the system, those properties will always be there. So that's the second answer. So whenever I'm doing the measurement, actually I would have to bring them together so that they would not be, you know, single stuff that have nothing, right? They would have some property that, you know, like energy, charge, and so on, and then I would measure that quantity particularly. Exactly.
Very nice. So single particle entanglement would be okay with these objects. Very nice.
Right, exactly. So after I did this rotation, so my Hamiltonian would look like this, right? Minus IVF times del over del x sigma y plus m of x sigma x. Now let me just write down the Hamiltonian in matrix form. Matrix form, it looks like this: 0. And then I have sigma y, so I have here minus VF del over del x plus m of x, and then here I have plus VF del over del x plus m of x, 0. And then I want to have this, so I want that h phi is equal, this actually is equal to acting on a state. I want this state to have zero energy. That's the condition. So now the fun thing is that it looks like you know, something that for particle only for this zero mode, you see that what is special about it. For every other mode, every other finite energy, I have to solve two coupled first order differential equations, which is equivalent to a second order differential equation, right? We know all about second order differential equations. It's essentially like as hard as solving a Schrodinger equation. Except when if you have zero mode, you actually have to solve a first order differential equation. The first order differential equation is principally solvable, you just integrate it, right? So you actually can see that the I would have a zero mode would have a solution like plus minus VF del over del x acting on my plus m of x acting on that some function f would give me 0, right? So any solution like that would do. So now let me just go carry this like that. So I just go plus minus, right? Then actually let me just put VF as well on this side. So stuff looks a little better. You actually have a direct solution, and I hope so. I will just leave you this as a homework, but I suspect most of you did it before. But if you haven't, do this as your homework problem number 1. Show that the solution is basically something like some normalization e to the plus minus integral m of x prime dx prime over vf up to point x. Okay, so that's great. So now you see that actually the only thing is that Griffiths is you know, you're going to now invoke Griffiths. So the Griffiths tells you this method that you can always have local solutions. This is a local solution. Locally satisfies your equation that you want to solve. Now what you want is that you want that this equation is normalizable. right? It means that it has to decay in both directions, right? Only then it's an eigenstate. You can always find local solutions. So that tells you that actually in this case, so depending on your m of x, right? So if your m of x, we got it to be something like this, right? Remember? So as you go to some m naught, as x goes to plus infinity, you see that that integral x m of x prime dx prime would go like some m naught times x prime. Okay, so if m naught is greater than 0, right, I would better choose the negative sign right here. So the plus sign won't do because it will give me a negative. So now here comes the negative thing about the negative sign. If you had an integral like that, x m of x prime dx prime, right? If you look at it as x goes to minus infinity, right? If you had been, and this would go with, now in this case, minus m naught, right? So this goes like, basically, it won't go like m naught times x prime, right? It will go like basically minus m naught times x prime, x prime. So which means that, you know, as you get, remember x is negative here, right? So it's a positive quantity. So as you take the minus sign, your wave function is also negative as long as you have a sign change. If you don't have a sign change, right? If m naught is, you know, here, this m naught is, instead of this m naught, I take something positive, right? 1 plus m naught, then I would have this changed by plus m naught times x. In that case, this will just blow up as you go to the opposite direction, okay? Because x would be negative, so then you would not be, you know, you would be decaying on one side, blowing up on the other side. Only when you have zero, that basically that change in the sign, you actually have the 0. Then you see that the only thing that you require from this m, you know, so if you have this m, so instead of this m, you look at another m that looking like this. Let's say not like that, but, you know, doing all this, but then going into the something similar, or you even get another one, you know, something actually coming from here, doing whatever, and then going to another thing. You would find out that as long as you have this one sign change, you would have the 0 mode, and you have one and only one 0 mode. This is the construction. So now this is the and the fact that, and people, when people talk about this, you know, the language, at least in this field, is such that when you say that, you know, you're changing your m from this particular value, particular shape to another shape, you say that you're deforming your Hamiltonian. Essentially, you're deforming your potential, and that potential is, what's it doing is that potential is, even though you change your potential, as long as you don't change a certain asymptotic limits, you'd never change your 0 mode, right? So then here you can say that the number of 0 modes, or sometimes called the topological index, right here is exactly the sign of m at positive energy times the sign of m at negative energy, okay? So the fun thing is that now we started out asking this question about plus and minus thing, that we see that if our universe had negative m, somehow, or, you know, if you actually made a mini universe or mini region, right, which can be a metal, or, and that's exactly what we're going to call that, it's a topological insulator of region of this negative m, the boundary you would have the 0 mode. Okay, so there are like some questions. Hocam, why do we have this kind of function m of x versus x graph? Have some kind of function in m of x? Well, it's just basically we say that, you know, you have this mass, right? So you have to go to, on this side you have an insulator, and on that side you have an insulator, right? So now let's just say that you know, since you have an insulator, both sides must have a gap. So now we have both sides having a gap. Then you have two options. You can have both gaps having the same sign, right? It's the same mass sign, or they don't have the same sign. And then in between, in the interface, your potential, whatever your mass, can be doing anything crazy, and that's not going to change anything. I hope that explained, that answered your question, Alijan. Don't hear. Yes, Roger. Okay, great, wonderful. Okay, great. So now that's the thing. So what I would want them to do is that I'm kind of running out of time. So now this is the general idea. Now I have the zero mode that is very stuck at zero energy, and I saw that actually a couple of things. So first of all, you see that this structure here was really important in arguing that mode is stable, right? Once it is there. And the second thing is that that structure, and then the fact that I could actually write everything in this form, and then such, and then when I'm looking at the zero modes, I actually look at this basically by instead of solving a full Hamiltonian, I actually solve a part of the Hamiltonian was the second part. Actually, these are parts of the stuff that is actually coming from the symmetry structures of the Hamiltonian. I will come back to this later. But what I would like to say here is that you typically, instead of looking at this Hamiltonian, you could have looked at that Hamiltonian, anything operator A and an A dagger 0, 0, right? So the thing is that you look at the Hamiltonian like that and looked at the zero modes, you would see that actually zero modes have either A acting on the sum phi minus is equal to 0 or A dagger sum phi plus is equal to 0, right? So now the important thing is that we know that if they come in two, right? So if I have one and the other, I actually can, I see that if I do some perturbation, I might be able to split them apart, right? So, but then if I actually have one and not the other, then I won't be able to get rid of that. Actually, this is actually a known fact, and people typically talk about the following, right? So they talk about the number of zero modes of A. They call it dimension of the null space of A, and then you kind of look at the dimension of the null space of A dagger. You look at these two differences of those things, and you call that an index. Right? It's called the Fredholm index, and it is that index is a topological invariant, right? So the number of zero modes of A and the number of zero modes of A dagger, if they differ, by 0, anything other than 0, those zero modes will be protected. Right? So that's the idea, and the way it's protected is something structured that I've been showing you. So whatever is happening locally, if you locally change the potential and so on, call that deformation, you're not going to change the index, topological index. You might change the topological index as you change let's say you take the asymptotic limit of one of your mass and you slowly lower it down, and then when it crosses 0, you see that you made a transition. And at that transition outside, you didn't stay an insulator. So this is also an overarching theme in these topological phase transition. Then we say that the outside had a topological phase transition. So this was in 1D. Now, what can you do in 2D, right? So the 2D is also, you can actually guess, if you start out from some sort of two bands, right? And then you want to search for something like a band crossing point, right? You might imagine that you want to have these band crossing point like that, right? So you would have a situation. And then when you have the mass, right, in our topological mass, or then actually we talk about a gap, right? So you would actually have a gap here, right? This happens a lot of times in 2D. So now again, the same question. So there is a parameter that tells us about this gap, right? The typical Hamiltonian that you can write is, remember, without the mass, I must have some sort of a cone, right? So I must have something which is 0 at 0 momentum. So then you can see that you can write it as some px times sigma x plus py times sigma y, right? Because I'm talking about two bands still, that's the most general Hamiltonian I can write locally in that energy range. Plus I would have some mass times sigma z. Okay, so this is basically for those of you who've been working in graphene and maybe other things, actually would recognize this Hamiltonian immediately. This looks like, for instance, a graphene in a single cone with a staggered potential and so on and so forth. So now, so what I would like to say is that, so typically, if you talk about then, we'll come back to this again. So just rest assured that this is a situation where you would be able to see a lot of times. Now, let me just talk about the following, right? So now I would like to start from this Hamiltonian, right? So now the same, I would want to play the same trick because I want to make it look like the previous Hamiltonian, right? I would like to make a rotation from Z into Y, right? So now this would, if I make a rotation, right? That's my rotation. And if anybody's interested, we can just figure that out in a second, but I don't have a lot of time. Just, you know, should be clear that and just like take my word for it, this can be done really easy. So now, of course, any rotation around X won't change this one, sigma X. If you rotate sigma Y, right, so that went into, so if you rotate sigma Z into Y, sigma Y, then your sigma Y rotates into minus sigma Z. Right, so this is sigma Z times Py. And then you have the mass times sigma Y. Now, this looks exactly like the previous Hamiltonian, H1D. And then you have another term, sigma Z times Py. Right, so now that's the critical thing here. So now you see that that 1D, right? This Hamiltonian has a zero mode, but you know this guy is going to shift it, do something with it. So that's what we want to see what happens here. So what happens here is something very cool, and that comes in because you know again we asked the question. Remember, this Hamiltonian is this Hamiltonian. If you remember, this is Px sigma x plus some m times sigma y, and I'm again going to talk about a boundary in x direction, right? And then, but then the mass now is of course a 2D thing, but I'm going to assume that my mass is just a function of x, right? It's basically start out here, and then it changes sign along the way at the boundary. Right, so you say that this is m, you know, less than 0, and this is m greater than 0. Okay. Now I know the solution. Now the fun thing is that remember that solution, and I'm going to leave this as a actually, if this had been like much more interactive, I would have asked you to figure it out immediately. But I would like to tell you in a second how you can find it. Remember, this guy has a solution, right? Zero mode solution, and that solution looks very much like this with the minus sign here, right? Remember the minus sign, right, will solve the equation. So if I take the derivative of this with respect to x, that will drop me basically a minus m of x. So that has another minus. So this will not be the solution. It will be this. Hopefully I'm right. Right? I don't know. So if I'm wrong, so just correct me, write this. So this is your immediate quiz, right? If I look at this combination, right, this VF del x plus m acting on e to the minus integral m of x prime dx prime of x, this is equal to 0. Right? So it's that one. So the solution here would have to have the form, right? Let me just call this solution the plus solution. Or if you want, let's say the minus solution. All right, so this is basically the solution here would be 0 and f minus. Okay, I'm sorry, f minus and 0, the opposite. Good. So now you see that the solution, therefore, of this guy having a 0 mode is exactly of that form, right? F minus and 0. Now let's have a see that what happens when I actually act on it with that Py, right? Remember, everything is homogeneous in the Py direction, so I actually can use a solution like e to the I ky times y, right? If I act on it with this whole Hamiltonian, I see that this part would give me 0, nothing there, and this part would give me basically minus sigma z acting on this f minus 0, right, times basically h bar times ky. Right? It's very easy. And remember, sigma z acting on this would give you +1. This actually is an eigenstate of sigma z. Right? You would find out that this energy would be actually minus h bar times ky. And then I don't forget the vf here. Remember, I kind of skip my terms. VF is there, so that would be h bar kf times VF. Right, so this is a really cool thing because now this tells me that my band structure looks very much like this. I have the gap here, I have the gap there, right? And now, in between, I actually have something that has that is a left mover. I have exactly one guy when Py is equal to 0. Remember, it's a function of Py. This is a function of energy. When Py is equal to 0, we have to hit exactly 0 because that's the zero mode that we found out. Now you see that zero mode is actually shifted, but it's always shifted proportional to Py and not minus Py. That's a really cool thing because it tells you that there's something at the boundary that moves only in the minus y direction, right? If I draw this here, I will draw it by saying that I have a mode that moves down here. Now, if I actually did the calculation on this side, where I actually again have m greater than 0, I would find out that this mode would be actually moving up. So now comes the second cool thing, right? If you have a mode like that, let's say at the boundary, right? So this is your, let's say, this is your mode. And then you actually had a boundary here, right? So this part, you did what you did, but here you got a, you made a bump like that. So now what happens is that if you solve this equation again, you would find out that this mode actually just goes through that bump. And the reason is very simple. You actually have a very simple scattering problem. There's only one in state, which is the in thing, and there's only one out state that goes out. And whatever is happening, you cannot do anything with it. You can maybe give it a phase or something. Right? So that's why everything works. And then you actually see that that chiral node would actually go through all the turnaround or the corners and so on. Right? So this gives you another property of this thing, and you actually have some sort of number of edge modes, which means that you basically, if you have make a setup like this, right? So those of you who Smith is not here, but if he had been here, he does these things all the time. Right, this is called sort of a region like this. So this is my outside. So this is basically called a whole bar. You would find out this edge state would actually go here. We'll come back here and go to this thing, and then it will go through. Now, if you actually inject current, so you typically say that you have a reservoir here and another reservoir there, and then you inject current by increasing the chemical potential of the edge states. So that will, what it does is that you actually see that you have stuff, electrons will be populated in that state. And then you can, of course, measure various things. You can measure basically the potential drop here. So you basically inject some sort of current. You can you might measure a potential here, right? This is kind of the longitudinal one, versus you can actually measure a potential here from here to there. So that's called basically the whole potential. Right. So basically what this does is that if you do this thing, you see that you find out that you actually have a whole potential, and that whole potential would be exactly quantized in units of conductance quantum. Okay. So then, and here normally you see this situation like this with magnetic fields, and with magnetic fields actually the state that you get is also topologically similar to a state like that. And this is basically called the quantum anomalous Hall effect. Okay. So now those edge modes that are protected, right? So therefore so remember the protected here means that, they're all protected as good as your gap, right? If your gap is tiny, they're not that well protected. If that gap is huge, right? So then you actually can, so for instance, if you could make a topological insulator with a gap like the electron's rest mass, that would be basically very, very, very robust. But if you make a topological insulator with a millivolt gap, that will be less robust. If it is even smaller, then it will be even less robust. You have to go to where, you have to be very careful to be able to measure it. But the idea is that as long as you're in that limits, as long as that gap, you're doing physics that doesn't touch the occupied bands, so that, that they don't contribute to transport and so on, this can be done. You can see this state. So now that is then the 2D version. Now the question is, before actually, since I'm not doing so well on time, I would like to actually talk about some extremely important part that overarching theme here. So you basically have, then you can ask yourself, so I was going to talk about the 3D version. So if I have time, I will come back to that. But the main idea is that in the 3D version and so on, you see that as you go up, you can, if you have a topological state, so that's the basic general, what we learned so far is that you actually have a region, right, which is an insulator, and another region, which is another insulator prime. And then if normally insulators are boring stuff, but they actually, turns out they actually classified by these numbers, right? So what we found out, for instance, when the mass is negative, for instance, and remember the mass is the gap value. So remember, I don't call gap because gap being negative doesn't mean anything. It's still a gap, but it's the parameter that gets map gets negative. So now, if that happens, then you have a situation where you would actually get, you basically can have a situation where those two, at the boundary, you have these topologically protected edges, right? The number of those edge guys is called the topological index, right? So we found the number of modes is a Preparatory index. But they're actually, sometimes people talk about, when they talk, you can actually, at this point, you can say that it's all topological because we have actually some sort of Hamiltonian, we deform it by, changing some local properties. As long as that remains local, that doesn't change the index. But actually, there is a little bit more geometry in this. And that geometry comes in because, for instance, in the 1D case, you talk about, for instance, our Hamiltonian, right? Our Hamiltonian is something of this form. You have a D times a sigma, right? So it's basically a vector that's multiplying sigma. Now we said that my Hamiltonian would have this property that sigma, z, it said sigma x at the time, but after rotation that would be sigma z, h sigma z is equal to minus h, right? So this tells you that there cannot be a sigma z term in there. So you actually have two d's, right? You have dx and dy. Now, which means that basically the length, if you look at the eigenstate of this, it will be proportional to d hat. And then you have actually Brillouin zone. Let's say, even I talked about the infinite system, but you can think about it basically a real crystal. In that crystal, you would actually, of course, your momentum space would be finite, it would have to periodically repeat itself, right? So you have actually a Brillouin zone that's coming from those two zone boundaries. Remember, that is a 1D thing, so this is how your K runs. Now, as your K runs, your D would have to go, change in a 2D plane. Right, it's a unit thing. So whenever you see that, and then you see a periodic thing in the momentum space, which means that you make a ring, at least topologically, out of your momentum line. Right, this line actually you can think about this as a ring here. Right, so this is the end of the Brillouin zone. It's the end of the Brillouin zone. They're touch, right? They're the same point in this. So now the important thing is that you have a map, and that map actually, remember, it is a situation like this. You actually have a string, you put needles on it, and then you basically wrap it around a certain thing, right? So that thing would actually have a winding number, right? So how many times that thing winds as you go, making this one round here. So that number actually tells you if you are in the region with the negative mass or the positive mass. Right, so that's exactly what gives you the index. This is topological index that you can get out of this, and the formula is actually is very simple, right? So that index is given by something like this: the unit vector cross del k, the unit vector dot z. Remember, this is a cross product, so I have to get it and thing out of that, and then I integrate it over the Brillouin zone. Right, so this index would be precisely related to this quantity. Okay, so now that also brings me to another interpretation of all this, because remember, this looks like very much like a spin, and then you basically have a momentum as you change the track your momentum along the thing. Your momentum is, we are saying that your momentum, as your momentum change, your spin has to track the momentum. And so this is a kind of a very strange constraint, okay? right? If you look at the band structure of this, you have to remember the energy values of this would be plus minus magnitude of D, right, as a function of K. But then as you go along in K, this would basically give you all sort of spectral rotations. Okay, so now, and that is precisely related to the Berry curvature. So it's the Berry phase. So the Berry phase, I don't have to, because the previous speaker, Barış, thankfully spent a lot of time on how you can actually do these type of things. So the main idea was, remember that you actually had a Hamiltonian, right? And that Hamiltonian basically had a discrete set of, had no degeneracy, nothing crossed each other. They all of them had degenerate levels, and then had a parameter, which, parameters are I, and then you actually had everything would have a set parametrically depending on all those Ri's. Now the adiabatic theorem tells you that if you actually start out so these are the instantaneous eigenstates, you start out with one of these instantaneous eigenstates, and then you adiabatically, very slowly change one of those parameters. Your state actually keep on following this phi Ri, but actually it will pick up a phase, right? And that phase, right, e to the I times basically some A of R dot dr, right? So, and this A of R is basically I times basically phi n's of times grad R phi n. So I put it in this form because it is not, remember, this gradient here is not an operator, right? It is basically, it's basically, you have a state and you basically take derivative of the state in the state space, right? So that's the thing. So it's not like it's an operator that maps the thing on another thing, but you basically literally, it's not, what I'm trying to say, it's not a momentum operator, right? It is like those, it's an operator that acts on the parameters of that state itself, okay? So now, looking at this, so you have this quantity here. Now there's a very amazingly fun thing that if you make so this is kind of looks like a gauge field, right? And then if you try to make a, ask yourself if you go through, all those things that you might have played with, when you were learning about basically, you have a conserving force, right? You have a situation like this. You have a line integral of some vector field. If it is a conserving force, this will give you, regardless of the path you take, this will always give you the same thing. And here, if you can ask the condition, if this is the case for A, when that's the case, we say that A is a trivial gauge. It doesn't actually give you anything. If that is not the case, right, and that means that your A has some sort of a, well, I'm kind of here assuming 3D, but you can actually write it in, so which means that I have Rx, Ry, and Rz. And then you can actually, this R, you can actually look at this quantity here. Right, this quantity not being equal to 0, right? This is, if you want, it's a vector, right? This is called then the Berry curvature. So if this thing is non-zero, you cannot actually get two different paths and then assume to get the same phase, which means that if you make a cyclic evolution, you would make a pick up a phase from this. And the fun thing is that you can, of course, that phase would be proportional to the area integral of this B, right? This would be kind of, if you want, the Berry flux, if you want to take the language from electromagnetic theory. Now you can also say that you integrate this B, right, over some entire available area of your thing, right, over the entire thing. That might give you something very interesting. Right, so this is the question that we would want to answer, right? So this is basically your, if this is basically around some domain D, you know that this is some A dot dr along the boundary, right? So Stokes theorem works and so on. So now this is for generic parameters. Now we're going to talk about when those generic parameters are momentum space variables. Okay, so what we're going to do is that we're going to look for a case when these R's are all replaced by K, right? So this is what we were doing, right? Remember, our texture of the of the spin would change as I move along in the momentum space. Now, because of that, I will be looking at this in terms of this K, and then I actually have everything that I did carries on here, except that now this Berry curvature would be a function of this K, right? You integrate this up, right? So this is that's the general thing. So if you're in 2D, right, this would be always be looking outside, and then you integrate this over a dA. Yep. Over an entire Brillouin zone. Remember, everything is compact on that. That will give you a number, right? This is equal exactly to 2 pi times topological number. Well, I don't know what you want to call that. It's the W, right? Or this basically is the topological index. So this is the, and yes, as usual.
So in connection to Barış's work, why do you need adiabaticity here? Why
you don't actually need it. For the definitions, you don't need adiabaticity. But it is, so the main idea is that, the way that we can think about is that, in a sense, we're adiabatic because, we basically have these two, let's say, so actually it's a nice thing. So imagine I have this upper band in momentum space and a lower band in momentum space, and they all have slightly different textures, right? So now, of course, if I have, let's say, certain things, these might, maybe exactly the opposite. So now the essential idea is that when my electron is stuck in the upper band and doesn't talk to the lower band, right, as it moves around in that thing, then it will be affected by the space. And that is kind of, it's not quite the same adiabaticity, but it is the same adiabaticity idea. You don't want that it's mixing up with another band. Okay, so that's the general idea. We're not talking about, we don't want a gap necessarily, but then we want that those bands are separated by gaps such that, they are, all the action takes care in the one band.
So can you also speculate if any shortcut will help here for some reason?
Yeah.
Like this contra-adiabatic derived term, if we derive it for this particular.
Well, I mean, the most obvious thing is the following, right? So you have instead of avoiding crossing by changing the Berry phase, you get an exact crossing from one to the other, right? Which is this one. This one right here.
Mm-hmm.
Right, so you basically, instead of going through, like one and then staying down here, if you're in a particular path, you would actually go up there, which actually is it happens. People call that charge pumping, right? So you basically can, use this to controllably pump stuff, and that amount of charge that you pump would be always quantized because of this and so on.
Nice.
So I mean, that would be, I guess, the most obvious thing. But I mean, it's an interesting question, so worth thinking about more. All right, so now I'm kind of running really out of time, and before I go anywhere, so I would like to talk about two things. One is that remember there are two overarching themes. So I talked about this basically. Well, remember, this is not a proper lecture to understand all this. This is more, to have a general feeling of what is going on. And if you have any questions and if you're interested, we can discuss it later. But the general overarching theme was the following, right? We had this kind of indices, which you can say that you can define them through basically looking at the Hamiltonians, but you can also define it through some geometrical means, looking at the integrated Berry curvatures and so on. So that will tell you, and those topological indices tell you what happens at the edge, like how many, like if you have a boundary with the trivial stuff, how many of these quantum states are forming at the edge. Okay, so that was the other thing, and the fact that you actually that number and this number coincides is called bulk edge correspondence. Okay, so depending on whatever the number that you have. Like from a bulk amount, right? From a bulk calculation, looking at the this Brillouin zone integrals and so on, you look at what's happening. You find out what's happening exactly at an interface, and how many protected zero modes would come out there. Okay, So that's and that actually in mathematics, there's a beautiful theorem that actually shows this one for the first time and similar things. It's called the Atiyah-Singer index theorem. That is actually is the very first one to actually make that that connection clear, looking at the geometry of basically the fields, and you're looking at your Hamiltonian, you calculate a topological index, and then you calculate also an index like a Fredholm index from your operator, and then you say that those zero modes actually those indices would be equal to each other, which is an amazingly deep theorem. So now these are basically generalizations of that or applications of that to various things. So now the important thing is that you remember the fact that I could write those things was a very key thing. So there's a question: can we say that the cause of those index being invents at the adiabaticity process of the TBAE curves? No, the idea is that it is not. So the only adiabaticity, there's an adiabaticity here left because there's no real time dependence, right? We talk about whether we have a state or not. But what is there is the following, right? So you want that everything here is protected by that gap. Remember, adiabaticity was also protected by a gap, right? So if there are all the states are nearby, come mixed with stuff, then your adiabaticity break down. If you have an enormous gap, then everything looks adiabatic. Now here, in that sense, this is also protected by a gap, okay? So if you don't have if the gap is very small, or if you kind of make transitions from up and down, then you would, of course, you would actually, I haven't given you, but that's one of the homework problems. If you calculate these Berry curvatures, you calculate for a band. You calculate for every band, and then you sum them up. That gives you zero, right? So all these effects are actually disappearing as long as you're not in a single band, right? So in that sense, it is not an adiabatic. There is no adiabaticity involved here. It's just like a way that you come to understand those phases. And in fact, for Berry phase also, you don't need adiabaticity either, right? Then it's called a different Anandan phase, but you actually can have a cyclic quantum evolution, which is not adiabatic, would still pick up a phase which is geometrical, in addition to a dynamical phase. So even there, the cyclic quantum evolution would pick up a phase which is also in part geometrical, even though you don't have adiabaticity. So adiabaticity here is not required, right? The only thing that's required is that you have a sizable gap. I hope that answers your question. So now the final thing is that I'm kind of running a little over time, so I will stop right after this thing, and I'll give you actually after that an interesting classical example of all this. So now the second thing is that, remember, the one thing was like I was able to work this out because I was able to write my Hamiltonian in off-diagonal form, right? That structure actually turns out to be extremely important. And that there comes in basically this thing called the tenfold classification. So this actually starts out from, I was actually at a nice picture of Inanu and Wigner, but since we don't have a lot of time, I won't go there. But remember, the Wigner was we talk about all the time those symmetries, and Wigner was the one that was actually interested in them. And then actually he made the first classification of the Hamiltonian. Actually, he was interested in S matrices and unitary tangible. I mean, in a sense, when you look at the Hamiltonians, if you had all the unitary symmetries, right? Remember, unitary symmetries you can use to block diagonalize your Hamiltonian, like we do in angular momentum. Now you did that all, and then you have all that you're looking at the single block. So now all the symmetries are out, and all the rest is broken. Right? There are no unitary symmetries left in the Hamiltonian. There's still some symmetries left, and now those are the so-called anti-unitary symmetries. And those are basically symmetries that tell you whether your Hamiltonian is whether your Hamiltonian is, for instance, real, or it is complex, or if it is, has some, or quaternion real, and so on. So we actually have real reasons for that. So now your Hamiltonian, we say that, for instance, if it is real, right, H star is equal to H, right? This is a real Hamiltonian. We call that, basically that you have time reversal symmetry. Okay. So the time reversal symmetry here is an anti-unitary symmetry. You have the complex conjugate, Hamiltonian complex conjugate is equal to your H star, and you want that this is equal to your H. Okay. So time reversal symmetry, of course, this is time reversal symmetry for a spinless particle. If you had a time reversal symmetry for a spinful particle, you would usually say that where time reversal symmetry operator is actually sigma 2 times k. Right. So this has the feature that actually, so So this is for basically spin, and the other one is no spin. But this is what you learn. But if you think about, if you just want to talk about generic Hamiltonians, you don't actually need all this. You just have one property that tells you that you take the Hamiltonian, right? You take the complex conjugate, and then you make some sort of unitary transformation of this. If you can get this to be equal to your H, then you say that you have some sort of anti-unitary time reversal symmetry. Right? It's a more general thing. And the fun thing is that you cannot have two. Okay, if you have two anti-unitary symmetries, the product is a unitary symmetry, but we didn't have unitary symmetries to begin with, right? So that's why you cannot have anything else. So the second thing is that important thing is that if you take this, and if you take t squared, you would get -1. And if you take this, and if you take t squared, you will get +. Remember, we all know this, because if this is the case, remember, we have every state comes in pairs, right? Called Kramer's degeneracy. I'm hoping that you all know this. If not, write it down so we can talk about that later. And if you have this symmetry, then you of course have you don't have Kramer's degeneracy, right? If you have no anti-unitary symmetries, you tend to have really like isolated eigenstates. Now Wigner was interested in this. There were also people who were trying to understand the structure of the nuclei, and then you come up with this most general random Hamiltonians and so on. But we're not going to go into that. So now, in addition to that, we actually have another one. Remember, we cannot have another anti-unitary symmetry, but we can have another one that actually tells you the following. Instead of this, I might have C H, let's say C inverse H, C is equal to -H, right? The time reversal, remember, mapped Hamiltonian, real part of the complex conjugate Hamiltonian to itself, this maps it to -H. What this does is that it actually tells you that for every positive energy, there is a negative energy state, right? So this is the particle hole. That's why you have the charge conjugation sometimes. That's the usage. So then you have this symmetry as well. Now the fun thing is that you have this, and this symmetry, lo and behold, might also have this property. C squared can be plus or minus 1. Right? Remember, t squared can also be plus and minus 1. But then also, of course, you may not have these symmetries. Right? So now you have this thing that you have these symmetries. So which means that basically you can classify your entire Hamiltonians by looking at these structures. Right, so remember, the charge conjugation is not necessarily there for semiconductors, but they actually sacrosanct. You have to have some sort of charge conjugation for superconductors. That's why sometimes some of those things are called basically superconducting things. But we are going to talk about superconductors tomorrow, so that will be part of this. So now the important thing is that if you have, excuse me, just like excuse me, we're running out of time, I think, right?
Maybe at some point we can stop, take questions, and leave the remaining part for tomorrow. What do you think?
I will actually say one more thing, because I don't want to come to this point again, and I will stop. So now, remember, t squared being -1 gives you degeneracy. C squared being -1 doesn't give you a general degeneracy, except it gives you a degeneracy of the zero. So, there are all sort of things like structures like this. We can discuss that later. But the important thing here is that, remember, I have this C symmetry, right? Can be +1, -1, 0. There's a T symmetry, can be plus, so there's 3 options. So basically, corresponding to them, you also have a symmetry times C times T, right? That's a symmetry, which is a unitary symmetry, but which anti-commutes with the Hamiltonian, right? You call that basically the S. That I think, for in condensed matter, typically people talk about sublattice, but it is actually and then other people talk about other things, chiral symmetry and so on. But the main idea is that here is you have S inverse H, S is equal to -H, right? So corresponding to that, you can have this possibility of you can have this S based on C and T. So now you classify your entire Hamiltonians as whether or not you have time reversal symmetry, 3 options. whether or not you have charge conjugation symmetry, 3 options, multiply them, you have 9 options. And then you can actually have, remember, there's only one additional situation, and that relates this, this CT symmetry. And that is the, and that's basically the chiral symmetry. It can be that you have either C is equal to 1 and T is equal to 1, therefore TS is equal to 1. You have both symmetries are intact, so therefore you have the chiral symmetry. But you can actually have this one special situation that if both are 0, their product is still a good symmetry. So that is the tenth. So if you take this, you have actually look at all your possible Hamiltonians, you see that your Hamiltonians are all possible ways, are 10 possible ways. That's called tenfold. If you want to, sometimes people call it the tenfold way to mimic the old older physics. Now, if you have this tenfold way, then you actually can look at your Hamiltonian and your dimensionality, and that will tell you what sort of topological states that you can have. Okay, so if you ask me a question, I can discuss that later, and tomorrow I'll show you. I was going to write it down, but we don't have a lot of time. But the main idea is that together with this type of structure and the dimensionality, for instance, you can say that the previous one of the previous Hamiltonians, we know that, for instance, it will either have an edge state or not. So that's a Z2 symmetry. Or you can look at quantum Hall. Then you can actually have many edge states. So then your topological index is Z, right? This becomes common with the numbers. So you can actually, by looking at the symmetries, you can actually tell what sort of topological index you might hope to get. And the second thing is that you have to calculate that index and get those edge states. And tomorrow, what we're going to do is that we're going to try to use that edge states for topological computation. So if I'm going to stop here. And if you have any questions, we can discuss that now. So please unmute yourself. Actually, if I can, I don't know if I can give that option to, so anybody can unmute themselves. Okay, Özgür Hocam.
Well, I have a simple question, so practical question. Is there any practical motivation to have more and more edge states for applications? For example, for quantum technologies or?
Yes, there is. I mean, in the sense that, if you think about, well, okay, so what depends on what business you're in. If you're in the Majorana business, you want them as you want one, right? Because you want to isolate a Majorana. So you don't want 2, 3, like people's talking about, you don't want to say that, oh, I have, 5 Majorana edge modes and then actually look, they hybridize and give me one as odd and so on. That argument is not good for it. So they want one. So they want to go as small and as isolated as possible. If you want to do other things, like let's say if you want to, for instance, use this channel to generate, let's say, pulses and things or spins to basically communicate information in a protected manner, then of course large can be good. So the problem is that the Z state, most of the time, the interested states are the main Z state is of course quantum Hall. But then quantum Hall puts you a lot of magnetic field, and people don't like magnetic field, right? They want a little bit of magnetic field. They don't want a lot of magnetic field, typically. So in that case, we know actually how to get that. But so people are actually more interested in Z2, I guess, or Z quantum, that is to say, or basically a Z state, but then looking at only one channel or 2 channels in that limit, basically.
Thank you, Inanç.
So actually, maybe if there are no questions, maybe I can ask you a question as a homework. So, and the homework is the following, right? This is we did all quantum, but now we're going to do something classical. And this is something that I hope most of you does, right? It's about this, it's a good exercise understanding this kind of like basically some sort of restrictions on our things. Right, we have a situation where we have, let's say, our spins, right? When they go through momentum space, they have to go through texture and so on. So that actually gives you that they all are restrictions, right? How does that restriction go in? So now here's a question. It's a very simple question because most of us do it inherently in our brains can handle it really well. And that is to driving a cart, right? So that's a very simple thing. And the cart is as follows, right? So here's basically a topologist cart. So you typically have those two wheels, right? So this is the endpoint. And then you typically have the part that you can, so you can actually think about the cart like as a cart in IKEA or something like that. So you can have the front, like the part that you can move, are the wheels that can turn, and the back wheels are fixed. Or you can think about a car. So there are two versions of this. So you actually can have a point X, Y here, right? And then you actually have this angle theta here. Now, these are the parameters that uniquely define your cart, right? So your parameters are X and Y and theta. So now, but then what you can do is that you can move this point, A, B, right? This is the point that you can move. So if you want to do the car piece, right? So you can actually say that you actually have a situation where you can actually have your wheels actually turn, so you can actually move in this direction. And in that case, you have another phi there and so on. But let's do the simpler version first, right? So you can actually move, let's just say that you can move A and B. So this basically is like any carts that you might find in IKEA or something like that. You have those wheels that can move on your side and the front wheels are fixed, so you can only push them and so on, right? So you cannot really move stuff. And that is the strange thing. You cannot move stuff to the side, right? The X, Y, whenever it's moving, right? So if you call this function n, right? The x dot, y dot, right, must be parallel to the vector n, right? So that's the restriction. So now comes the question. Well, actually, depending on how much time I have, I can tell you more, but so the question is as follows. So here it is. So this is actually, let me just start out in the X. So I start out with a cart when theta is equal to 0, right? So theta is equal to 0. Now what I do is that I take my position of this point and I make a little circle. Okay, of radius r, right? R is small, right? If you want to know what small is, if you say that this branch is D, you have R over D is much smaller than 1. Okay. Now the question is, what happens? So you can actually, have you ever tried this? It does something that looks like as if, you know, stuff that is not easy, right? So you see that your restriction is such that you cannot start out with your cart and then you can move it to the side, right? We all know that. But then by making this movement, you would find out that your cart actually rotates, right? So some delta theta. Okay, so depending, of course, remember, and that will be directed, right? If you do the circle in one direction, that would be one, you would rotate. Whenever you finish that circle, you would rotate in one amount. If you do it in the opposite direction, you would rotate in the opposite amount, right? So that is the key thing. Now, if you do this, you would find that this delta theta is actually, and this is the answer, and you have to show this, is equal to pi r squared. Right, in, you know, d squared actually. So this so this is your homework question, right? And the main idea is that if you think about this, is very much similar to what we talk about whenever you have these particles that are moving in those restricted quantum particles moving in those textures. Right here too, your spin is locked to those texture, and that's your restriction. And as you move around, you can actually pick up, but nevertheless, as you move around, make little like circles and things like that, you pick up non-trivial things, right? So this is why it is like, this is sometimes called non-holonomy, or the holonomy of this thing. So something is a non-holonomic constraints, in the sense that, you know, basically, for instance, if you have a constraint that your velocity is perpendicular to your position, for instance, then the restriction puts you on a circle, right? So that's an easy one, right? here you have a restriction, but it's not a restriction, doesn't put you, we don't know yet, but if you do this, you do the math correctly, you would find out that actually we don't need to do the math correctly because we know the experiment. We all use the cart, you can get anywhere you want. You can direct it anywhere you want in any direction. So you can actually fill up the available phase space, but then you just have to do it a little bit in a crazy way. And we all know this, right? So, and incidentally, you can do the car parking as well. And it's also something like a geometrical phase that you do some sort of a cyclic evolution. And what you do is that you do this parallel parking, right? So you can actually do this as well if you want to look at the more generalized version of this problem. So this is your question. So hopefully you'll enjoy solving it. And I'm basically gonna hang up now. Thank you so much.
Maybe we should also clarify that we are going to collect these homeworks and seriously evaluate them for maybe future organizations. So this could be some motivation, further motivation, and maybe we should clarify that in future we are planning to make some face-to-face meetings, hopefully. Then these homeworks may help to decide who will attend.
That you were serious enough and you were really interested and so on. It's a way to show your...
İnanç Hocam, thank you very much for this nice lecture.
Thank you as well.
So,
it was a pleasure.
As far as I can see, there is no more questions.
Yes.
So let us leave everything along with questions for tomorrow. For the time being, thank you everybody for coming, for your attention. İnanç Hocam, thank you for your contribution,
Thank you.
what you have done for the school. Make it successful, as well as all other lecturers, friends, and remarkable colleagues. So see you tomorrow.